In this demonstration, I will showcase the Distributed Federated Learning DFL framework. This framework consists of a federation of nodes that are deployed in Docker. These nodes can be configured in different ways in order to train a model in a decentralized, federated learning environment. It has different modules such as the explainability module, the sustainability module, and the trustworthiness module, and also a robustness module has been integrated as CRUM in order to produce more robust models. So when the federation of Dockerized nodes trains the models, they are uploaded to the global model repository in order to have a persistent save of these different models, metrics, logs, etc. so they can be retrieved by other partners. So now I'm going to show you the dashboard of the DFL framework, in which I'm going to show the scenario configuration. So starting with the topology, we can set a variety of topologies such as fully, ring, or random. We can also select different datasets such as NIST, TONIOT, or an IDS dataset. Here we can toggle whether the data is going to be distributed in an independent and identically distributed manner or non-IID. Also talking about the models. These are extremely correlated with the datasets. So if we want to use a NIST dataset to train a model, the model will be a multi-layer perceptron model. If we want to use a TONIOT dataset, the model will be a CyberNet model. And if we want to use an IDS dataset, the model will be a spiking neural network. We have also different aggregation algorithms, such as FedAverage, CRUM, ADMM, or DRS. Talking about the explainability, we can choose whether we want to explain the model using SHAP values, in the case of NIST, or if we want to use time series to explain the model using the TONIOT dataset with SHAP values. Now we can choose whether we want to use the CPU accelerator or GPU accelerator in order to train these models using the GPU or the CPU. And we can toggle whether we want the communications to be encrypted or not. Here we can set also the training rounds and the local epochs per node. Now here above we can see the topology that we are creating in real time. So if we add a node here, we will see here in the graph that a node has been added. Also, if we remove a node, the node will be removed. And now talking about the configuration of the nodes, we can select whether we want the nodes to perform as an aggregator or proxy. If we want the node to perform as an attacker, we can customize the attack's magnitude by putting less strength or more. Also, we can specify the fraction of the local dataset, and we can select whether we want the node to be the starter node of the federation or not. Being the starter node means that the node is going to wait till all the nodes of the federation are connected to it, and then it will send a message to start the federation process. And down here in the metrics dashboard, we will see the real-time metrics that the nodes are sending, such as the F1 score, the bytes that they are sending, CPU usage, etc. So in this use case, a third-party application could request a model training in a custom federation and retrieve a model training response when the DFL framework starts training the different models in the federation. So a custom federation will be created by the DFL framework using a configuration file scenario.json, and the dataset that we want to use by the previous configuration will be distributed in the nodes. Then we will start training the model, and the nodes will aggregate the updates of the different models of their neighbors. Also, this loop is occurring during the different rounds of the federation. And finally, the different metrics of each participant, and the metrics regarding the model trained by The participant will be saved in the GMR, the Global Model Repository. So here I am going to configure the scenario for use case 1. I'm going to use the predefined topology. The TONIOT dataset, the data distribution will be non-IID. Also, the model is going to be a CyberNet model. The aggregation algorithm that we are going to use is CRUM. Explainability is not going to be selected right now. And we are going to use a GPU accelerator. The communications are going to be encrypted between the different nodes. The Federation will be training the model for 10 rounds and 1 epoch, and also the nodes will be configured without an attack, so I'm going to run this scenario. Now, we are going to see in the metrics dashboard that we will have telemetry data such as the percentage of the CPU that is going to be used, the bytes that the nodes are going to be sending, and also the F1 score of the model that the different participants are training. So I'm going to wait till all the metrics are shown here. And then I will do a brief summary about the different metrics and a comparison between the different nodes. So looking at the real-time metrics dashboard, we can see that the F1 score has been scaling up rapidly. In round 2, we have a score almost of 0.8. So we can see that the model is reaching a high convergence and classification score on the TONIOT network dataset. Now I'm going to show how to interact with the GMR OpenAPI, and we can check the status of the GMR using this endpoint. So if we execute it, we can see that the GMR is running. And now, we can see that we have different endpoints to upload some data to the global model repository. We can upload models, metrics, images, configurations, and logs of the different participants of the Federation. So in order to interact with the global model repository, we can make use of these endpoints. So let's start with the first. The endpoint lets us retrieve all the stored scenario names and their configurations. So we are going to execute it. And as we can see here, we have the scenario that has been already executed and its configuration. We are seeing that this is the same configuration that we defined before in the dashboard. So I'm going to copy the name of the scenario in order to continue interacting with this API. And we can retrieve a more detailed configuration of the scenario. So if I download this file, I can see the configuration just here. And as we can see, it is the scenario configuration that we defined before in the dashboard of the framework, but in a JSON file. Now we can retrieve also the different logs of the participants. Download the file, and then we can see that we have the different logs of the participants. Well, as we can see in the log, there's more information about the process of the different nodes. In this case of the first node, the participant 0. So this is useful to know if there has occurred some problem in the Federation or to retrieve more data that is happening inside of the node. Now, talking about explainability, we don't have images of explainability in this scenario, so we are not going to get anything. As you can see, the API cannot find images. Now, we can download the metrics of the scenario. Also, as you can see, we have here the zip file with the different metrics, and we can see that we have the different .csv metrics files of the different participants. We have here the test metrics, the train metrics, their validation metrics, and the system metrics, such as the CPU usage, the bytes sent between participants, etc. And if we put only the name of the scenario, we are going to get all the different models of all the different participants. But we can use filters in order to obtain the best models by participant. Or maybe, if we want to get a model of the participant 0, one that has a greater F1 score than 0.8, we can obtain the models that have that score. So as we can see here, if we unzip the model files, I can retrieve the different bento models and also the models of the participant 1 that have a greater F1 score than 0.8. So let's move to use case 2. So this is the second use case in which we have the same scenario as before here, but then in the DFL framework we have two types of nodes. We have the benign nodes and the malicious nodes. For the demonstration, I will be configuring only one node to be a malicious node in the federation. So the dataset will be distributed in the different nodes and they will start training. But the malicious node will send poison weights to the benign nodes before they aggregate their model updates. And finally, the model metrics and the metrics of each node in the federation will be saved in the GMR as in the previous use case. So for this use case, I'm going to show two possible scenarios. A scenario in which we are going to use the FedAverage aggregator, and another scenario in which we are going to use the crumb aggregator in order to filter this attack produced by the malicious node and compare the results of both scenarios. So now in use case 2, as we can see here, we have the same configuration as before, but we are changing the aggregation algorithm to FedAverage. And one node of the federation is going to be an attacker and is going to perform a model poisoning attack with a strength of 10,000 and percentage is set to 1. So let's run the scenario. And now we are going to wait for the metrics dashboard. The F1 score of the different participants has dropped to 0 value, because the malicious node, which is participant 0, is performing the model poisoning attack, and FedAverage blindly computes a weighted average of all the peer updates, so this is resulting in the global model being completely useless. Now I'm going to the same scenario configuration, but using the crumb aggregation algorithm, which will result in having a more robust model, while a node is performing a model poisoning attack. So let's run the scenario and wait for the results. The F1 score of participant 0 is below 0.05 most of the time. This is happening because participant 0 is the malicious node, and what participant 0 wants is to destroy the other models of the benign nodes so they have a useless model. But this is not happening because, as we can see, the F1 score of the benign participants of the federation is above 0.8. And this is happening because of using the crumb aggregation algorithm, which results in having a robust global model. This slide outlines the sustainability flow of our decentralized federated learning framework, which balances privacy on the left with energy efficiency on the right. First, looking at the aggregation method, because there is no central server, we use mathematically grounded consensus algorithms, specifically ADMM and DRS. These allow edge nodes to securely collaborate with one-hop neighbors, ensuring the entire network remains still decentralized and privacy-preserving. Second, on the model selection side, decentralized training can be power-hungry. To solve this, we leverage spiking neural networks because spiking neural networks are event-driven and sparse. They only consume power when neurons fire, drastically reducing the energy footprint. Finally, we back this up with data. The framework continuously logs energy estimation metrics, tracking network sparsity, measuring actual energy consumption in picojoules. Now, let's see how this sustainability flow translates into the robust DFL framework dashboard. On the left, under Scenario Configuration, we can set up our decentralized environment. This is where we select our privacy-preserving aggregators, like ADMM, and tune parameters like the row convergence penalty. On the right, the node configuration graph visually maps our network topology. In this case, a decentralized ring topology linking our edge nodes. Next, for energy efficiency, by selecting the network security dataset, the framework automatically maps it to an event-driven spiking neural network model. We set our rounds and epochs to 5 and click on Run Scenario. Finally, to see the proof, let's take a closer look at these logged values. Now, I downloaded the metrics from the GMR using this endpoint and putting the scenario name. And now, looking closely at the generated metrics file on the screen, we can see the exact data the framework captures to prove its sustainability gains. First, the spiking activity ratio. This sits at a very low decimal value, confirming that our spiking neural network is highly sparse, and most of the network remained dormant during the run. Next, the energy SNN versus energy ANN. Here is the round energy footprint. The SNN consumes a fraction of the power measured in picojoules. Finally, the energy efficiency ratio. This definitive metric, by dividing the ANN baseline by the SNN energy, outputs an exact multiplier showing that our network runs significantly energy-efficient models. These concrete logs prove that the robust 6G framework successfully delivers sustainable, privacy-preserving intelligence at the edge. So in this use case, the main difference is that after a round of the federation, a trustworthiness analysis will be computed for the new model version. And this analysis will depend on which dataset we are using. If we are using the TONIOT dataset, we will perform a SHAP analysis with time series. And if we are using a NIST dataset, a SHAP analysis will be produced. So finally, as we will see in the demonstration, some explainability plots will be produced and stored in the GMR. Let's start with the explainability use case. In this case, I'm going to use the same configuration as before, but with explainability enabled using time series with SHAP values, using the TONIOT dataset and using the CyberNet model. Also, every node is benign, so there is no malicious node in this configuration. So now that we have all the explainability plots, we can see that we have the plots of the different rounds for each class, and we can see the heat map of the different features in order to see how the model is learning for each class based on those features.